Hi all, today we discuss the remaining theorems on linear independence in section 2.3. This is theorem 2. Uh, a subset of vector space V consisting of the single vector u is linearly dependent if and only if u equal to 0. So this is a characterization for again a linearly dependent set. So the characterization of linearly dependence can be used as a characterization of linearly independent set. So you can write this as linearly independent if and only if u not equal to 0. Okay, so this is the since this is a if and only if condition, you can replace this by its corresponding contrapositives. You can get the characterization for linearly independent sets. Okay. Now we will prove this. We have a set u, set contain only u. U is linearly, the set is linearly dependent. We need to prove that this is if and only if u equal to 0. The one part is very easy. When u equal to 0, you can write this as 1 times u equal to 0. Okay, so we have a coefficient c is equal to 1, and this is a vector in the vector space, which is the c is not equal to 1, but the combination is 0. This implies u is dependent, linearly dependent. It's the definition. The definition of linearly independence, c1 u1 plus etc. c and u1 equal to 0 implies each ci equal to 0, cn equal to 0. That means this is the definition of linearly independence of u1 u2 etc. un. Okay, so the u1 u2 etc. un are not linearly independent, means this u1 u2 etc. un are linearly dependent. That means whenever this combination is 0, you can get a non-zero scalars which are not all 0. Okay, that means there is a linear combination equal to 0 with not all coefficients are 0. So this is one such combination, 1 times u equal to 0. So coefficient is not equal to 0. That means the linear combination of u itself is 0 with some non-zero coefficients. So this shows that u is linearly dependent. The set u is also linearly dependent. Now you assume u is linearly dependent, then this is u is, the set u is linearly dependent. By definition, there exists a linear combination of u with non-zero coefficients. That means there exists a non-zero c such that c times u equal to 0, c not equal to 0. This implies u equal to 0. Since c times u equal to 0 implies 1 by c times c u is equal to 0, that implies u equal to 0. Since this c is a scalar with non-zero scalar in the field f, then there exists an inverse, that is 1 by c. Then 1 by c times c u is equal to 0. Then by associating this, you can get 1 times u equal to 0, that is u equal to 0. So this implies that whenever u is a single vector, u is linearly dependent, then that vector is nothing but 0. This proves theorem 2. Now we have theorem 3. A subset of vector space consisting of two distinct vectors, say v1 comma v2, is linearly independent. This is linearly dependent. If and only if, we need to prove that this is if and only if one vector is a scalar multiple of other. That means either this v1 can be written as d1 times d times v2, or this is some scalar vector, this is some scalar d1 times d times d1 times v2, or you can write v2 is equal to some d2 times v1. Okay, so this is the meaning of this statement, v1 v2 is linearly independent and one of these equation holds. So first you assume this v1 v2 is linearly dependent. V1 v2 is linearly dependent means so we first assume that v1 v2 is linearly dependent. That means there exists scalars c1 or d1, say we can say that c1 c2 not all 0 with the condition that c1 v1 plus c2 v2 equal to 0. Okay, so there are scalar c1 c2 or this the linearly dependence of this set gives the assurance of getting at least one non-zero coefficient from this expression. Okay, so one of them is always non-zero. If c1 with this condition we can either c1 not equal to 0 or c2 not equal to 0. If c1 not equal to 0, we have c this v1 can be written as minus c2 by c1 times v2, say d1 times v2. If c1 not equal to 0, you can transpose this to the right side and divide throughout by c1. Since c1 is not equal to 0, then 1 by c1 exists, then you can multiply the expression with 1 by c1, then you will get this one. That means v1 is a scalar multiple of v2. In the case when c2 not equal to 0, we can write v2 as minus c1 by c2 times v1. Okay, that is some d2 times v1. So this shows that the c2 not equal to 0 implies v2 is a scalar multiple of v1. So this proves the one part of the theorem. Whenever v1 v2 is linearly dependent, then one of these vectors can be written as a scalar multiple of the other. Conversely, you assume one of them, either v1 is equal to d1 v2 or v2 is equal to d2 v1. Then this implies we have this v1 minus d1 v2 equal to 0 or minus d2 plus v2 equal to 0. Then you can get from this 1 times v1 minus d1 times v2 equal to 0 or minus d2 times this v1 plus 1 times v2 equal to 0. That means you can get two linear combination of v1 v2 as 0 with at least one coefficient is non-zero. Okay, that means not all CIs are zeros. That means there exists at least one expression for linear combination which is equal to 0 including v1 and v2 with one of these coefficients is non-zero. This shows that v1 and v2 are linearly dependent. Okay, so this proves theorem 3. Now here theorem 4. A set of vectors in a vector space V that contains the 0 vector is linearly dependent. That means if you consider a vector, consider a set with a 0 vector and it contains other vectors like u1, u2, etc., some un, then this set is linearly dependent because of the presence of the 0. So how will you prove this is linearly dependent? We need to get a linear combination equal to 0 with not all CIs are 0. So once you consider a linear combination, 0 times u1 plus this 0 is a scalar, 0 times u2 plus etc. 1 times 0, this 0 is a vector, then you can get this expression 0 because 0 times u1 is u1 is always 0, 0 times u2 is 0, etc. The last one I'll write it as we can write the last one as 0 times un plus 1 times 0 equal to, when you evaluate this expression, you can get up to this, we have 0 plus 1 times 0 again, that is 0. So you can get this linear combination is 0 with C1 equal to 0, C2 equal to 0, and all the way up to Cn equal to also 0, but Cn plus 1, this is Cn plus 1, Cn plus 1 is 1, that times 0 equal to 0, where C1 equal to etc equal to Cn equal to 0, but Cn plus 1 equal to 1. So that means a linear combination of these vectors is 0 with one of the coefficients is non-zero. This shows that the set 0, u1, etc. un is linearly dependent. This proves theorem 4. Now we have theorem 5. If a set of vectors S in a vector space V is linearly independent, this is linearly independent, then any subset of S is also linearly independent. That means subset of linearly independent set is linearly independent. So we start with a set S consisting of a vectors of linearly independent vectors of V, say u1, u2, etc. some uk. This is a set of all linearly independent vectors. Now you consider a subset of this. What is the meaning of linearly independence here? Whenever you get an expression like this, c1 u1 plus etc. ck uk equal to 0, that immediately implies that c1 equal to etc equal to ck. All the coefficients must be 0. This is the only possible linear combination as 0. So this is the definition of linearly independent set. Now you consider any subset S1 consisting of some vectors of this set. If suppose this contains u2, u8, for example, this contains all the way up to un minus 1, u2, u3, u8, u10, etc. Some of the vectors from this set. So I call this set as an arbitrary set as un1. This n1 is some suffix from 1 to k, and etc. some uns. Okay, suppose this is an arbitrary subset like this. This is an example. Similarly, you can construct any subset of this S. So S1 is an arbitrary subset of this S, say un1, un2, etc. uns. This n1 is some of the suffixes 1, 2, 3, etc. all the way up to k. Now we need to prove that this is also linearly independent. Okay, how will you prove this is linearly independent? We need to consider a linear combination of this. So Cn1 un1 plus etc. Cns uns equal to 0. We need to prove that all these coefficients are 0. So once you assume this, you can rewrite this expression as 0 times u1 plus by adding 0 from the left side, you can replace that 0 by 0 times u1, 0 times u2 plus etc. Cn1 times un1, this is un1 plus etc. 0 times the other ui's, some ui plus etc. cns times uns plus etc. 0 times ck, 0 times uk equal to 0. So that means insert all the elements of the set S in this expression by putting the corresponding coefficient as 0. Okay, so the only coefficients the only coefficients of these vectors un plus un1, un2, etc. uns are termed as cn1, cn2, etc. cns, and all other coefficients are 0. Now you can get an expression like this. This is an expression of elements of S with some coefficients. But whenever this expression is 0, you can get all these coefficients are 0. In particular, this Cn1 equal to Cn2 equal to etc. Cns equal to 0 due to the linear independence of these vectors. Okay, so this implies that whenever this linear combination is 0, you can get all the coefficients would be 0, this is nothing but the linear independence of the vectors un1 etc. uns. So this shows that is linearly independent. Okay, this proves theorem 5. Any subset of linearly independent set is linearly independent. Now we have last theorem. Theorem 6 is the last theorem of this section. If a set of vectors as in a vector space V is linearly dependent, then any larger set containing S is also linearly dependent. That means superset of a linearly dependent set is linearly dependent. So that means if you consider set S consisting of the vectors v1, v2, etc., Vr, this is a set of linearly independent vectors, linearly dependent vectors. So we have dependent vectors. Now we need to prove that any superset S1 consisting of these vectors, that means that contains S, say V1 etc. Vr is also are also members of this S1, and there are some other members like R plus 1 etc. Vk. We need to prove that this set is also linearly dependent. Okay, then what is the meaning of linearly dependent set? This is linearly dependent means there is a linear combination of these vectors equal to 0 with not all coefficients are 0. That means there exists coefficient, there exists scalars c1, c2, etc., cr such that c1 v1 plus etc. cr vr equal to 0. Not all ci are 0. That means there are some coefficients of these c1, c2, etc. cr are non-zero coefficients. So once you got this one, you can easily construct a linear combination of these vectors, say c1 v1 plus etc. cr vr plus 0 vr plus 1 plus etc. 0 v k is also 0. Because this part is 0, because this is 0 times this, 0 times this, etc. So this implies that not all ci, that means coefficients, are 0. Because we have non-zero coefficients with this expression is 0, then you can easily construct for these vectors v1, v2, etc. up to vk, this combination is 0 with some non-zero coefficients. This shows that the set S1 is linearly dependent. Yeah, that means any superset of this S1, this S is linearly independent set is linearly dependent. But in the case of linearly independent, you can say that any subset of linearly independent set is linearly independent. The converses of these two theorems are not true. So I'll write. You can do an exercise. Prove that or by counterexample, converse of theorem 5 and 6 are converses of theorem 5 and 6 are not true. So find the counterexamples. This is an exercise. So find counterexamples for this to disprove the converses of theorem 5 and 6.